clear for everyone. Can everyone hear me? Yes, 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 yes. Okay, cool. So, deep learning. What, how, why, and I'm going to talk today about the use of deep learning, especially for Kaggle competitions, as this is probably the most interesting part, instead of the pure academic part. So, in about 45 minutes, I will explain to you what SMUF is, why SMUF is interesting, and why you really need SMUF. In about 30 minutes, I'm going to talk about bigger and deeper is better. In about 15 minutes, I'm going to give you some publicity on vanished oxygel and why it's important for deep learning. So, let me start. They asked me to give like a deep and technical talk. I had 1 hour to tell everything I felt like telling today. But first, I don't know what kind of audience I can expect here today. So maybe who knows what convolutional neural networks are? Like, raise hands. Oh, cool. It's okay. Who works in machine learning or would say that he works in machine learning? Okay, yeah. Who knows what Kaggle is already? Okay, it's like the big majority. Who has worked on Kaggle problems before? And who would if he had the time? Okay, cool. Who knows what dropout is? It's like, okay, so very deep. And who has worked with deep learning before? Okay, a couple of people. Okay, thank you. So I know what to focus on. Who am I? My name is Jonas. I'm a PhD student at Ghent University. I have very bad memories about this room. This is where I studied and did my exams. Yeah. You might know me from this. This is was on Twitch last year. Was the LSD neural network? It went viral. It's been in The Guardian, there's a New Scientist, stuff like that. I made this together with a couple of colleagues of mine. This was based on deep learning. So with deep learning, this is, for example, something you could do. So I made this with my colleagues. We are the former Reservoir lab. We are not the Reservoir lab anymore. So David was there from the beginning. Now we're a part of Data Science Lab and part of ID Lab, and this is a bunch of logos, Ghent University, Eris, iMinds, stuff I need to mention in my talk. Yeah, and so we did research in neural networks since 2005, right? And so we did it way before it was cool, What do we do now? We are focused on machine learning, and we do this in two bigger domains. We also focus on robotics and on how to use machine learning in robotics. And we also focus on brain-inspired computing. So we're in the Human Brain Project, which is really academic, but it's a project from the European Union on simulating a human brain in a big computer. What did we do and why am I here today? So with our team, we did, outside of the office hours, we worked on some Kaggle competitions. We worked on the Galaxy Zoo, where we came in first place, the National Data Science Bowl and the Data Science Bowl, which was a couple of months ago, where we came in respectively first and second. We got we won some money with that. And people from our lab, for instance, one of the guys who worked on the previous National Data Science Bowl, he worked now on the Go thingy, which was a couple of months ago, which everybody heard about, right? Yeah, so his name is right here on the paper. Here, Sander. So yeah, so I hope I convinced you I know a bit about deep learning. So for the people who didn't know about neural networks, I'm going to quickly explain it, but it was almost no one, so I'm going to go quickly through this. So what is a neural network? A neural network is made up of different neurons, right? Neural network is made from neurons. This is one neuron. So one neuron receives a bunch of inputs. From these inputs, it multiplies this by a certain weight. After this, everything is summed. Then you have an activation function, which is a nonlinear function. And then you have your activation of your neuron, which can then again go to other neurons and other neurons and other neurons. This is this is the very fast explanation of how one neuron works. Now, with one neuron, you can do nothing. So we make a bunch of neurons. You have like 3 typical names for the layers. You have an input layer, which is where you show the image to your neural network. Then it gathers along through hidden layers. And then finally you have your output layer, which is the classification or the output activation or whatever you want to be, whatever you train it to be, that's what is coming out of your output layer. And now we want to train this. For this we use gradient descent. Somebody here who doesn't know what gradient descent is? So gradient descent, you calculate the gradient of your error over your parameter domain, and you take a step in the other direction. And that's how you optimize through to the minimum. With neural networks, this is done with back propagation. And this is something, a small point of focus maybe, which is really important, is that in a neural network, when you have like for instance, if you want to know the gradient for parameters of neuron F1, then what you do is you look to the neurons which it was connected with, and then you calculate back. So when you want to evaluate some image, you show it to the left, you go through the image to the right, then you know what it predicted, you know the error, and what you then do, the calculation is just going backwards, and that's why it's called back propagation. Yeah, and this is how you do gradient descent in neural networks. So this is my short 5-minute thingy. Now, what is deep learning? Deep learning is in essence neural networks, but just like more neurons, like way more neurons. I'm stacking layers on top of each other, and this is why it's deep learning, is because you need to go very deep through your network in order to optimize the parameters at the end. A little bit of history, maybe, to indicate what happened, because artificial neural networks, they're pretty old. So they were invented, or they were mentioned for the first time in 1949 by Dr. Hebb, if I remember correctly, with Hebbian learning. So this is even before the first computers. People were thinking about how could the neurons in our brain work, and how could we maybe someday simulate them. The first step forwards was in 1975. In 1975, there was suddenly a couple of things which went forward, one of which was back propagation, so we now had a system on how to optimize these neural networks. And then it went silent. Then neural networks, they were cool. They said something, told us about how our brain might function someday, but actually they were not very useful. You didn't see them a lot for actual applications, right? And then suddenly deep learning evolved in 2012. Deep learning, bang, in 2012 they won the ImageNet competition, which is a competition in computer vision. Like, suddenly they beat all the classical ways to do computer vision, and deep learning is now the state of the art, is the way to go. If you want to do computer vision, do deep learning. Don't do SVMs or feature engineering or whatever have you. No, just deep learning. Deep learning is the way to go. I'm now going to try to explain you what the problem was. Why didn't deep learning work before 2012? What has changed? Because I think this is an important indication in what you need to do if you want to do successful, use deep learning successfully to deal with a problem. So if you look here, this is my big neural network. So if I do back propagation, so I went forwards through the network, yes, I have my error. And now I need to calculate the gradient back. There's a problem, because if I have my error here, I take one step back, yeah, my gradient will be still pretty clear. It will be clear, like this parameter needs to be higher, this one needs to be lower, right? But then I take another step back, and it kind of starts to look a little bit mingly. And another step back, and you see all these connections here, and the mingling has gone on, and it's not very clear anymore for this parameter. Does it need to go higher, does it need to go lower? And by the time you're like 4 to 5 layers deep, the gradient pretty much looks like noise. You cannot really say, like, does this parameter need to increase in order to have a better performance? Does it need to increase? You don't know. This is called the vanishing gradient problem. Vanishing gradients, and all your information is gone by the time you're back at the bottom of your network. This is the problem which you need to really deal with when you want to do deep learning. And for long we didn't know. Just how do you do this? How do you make sure your gradients goes through multiple neurons and still doesn't lose its information. What has changed? These things. So in 2012, for the ImageNet competition, these were the 4 main things people used, which make the big difference. One thing is GPUs, because you need just more computation power. In the 80s, the people didn't have the computation power. GPUs is one thing, but it's kind of boring. Academically, I mean, the GPUs are pretty cool. But the 3 other things are rectifiers, max pool, and dropout, because they fight vanishing gradients. They make sure your gradients go all the way through to the bottom of your network and can still learn there. I will try to explain you why. Deep learning. And that's why it's called deep learning, because you go all the way through the bottom of your network. And this approach can be used for all kinds of data which is spatially correlated, which I mean, for instance, an image. In an image, you have pixels which are close together. Pixels close together, they have mutual information which you need to extract. For instance, if there's a cat in the top left of your image, these pixels belong together and they have information together. You don't need the pixels in the bottom right to know, oh, this is a cat here. Other examples for this, or for instance, sound. Sound is locally correlated. And because you don't need to do feature engineering anymore in order to deal with that kind of data. This is a kind of old school bingo. I don't know if you heard about neural networks before. These were the type of stuff you heard about: Boltzmann machines, energy, 10H, sigmoids, feature engineering, deep belief networks, all those kinds of stuff. Like since 2012, we know that, well, they work, but not very well. So now we have way better approaches to deal with the problems we see in neural networks. How to do modern neural networks. That's what I'm going to try to explain to you in this talk. I hope you're interested in this topic. Yeah. I see some people nodding. Okay, cool. Yeah. So let's start with the beginning. You get the data, split this data and train sets, validation sets, and test sets. In the case of Kaggle, you already have a test set. That's a set of which you don't have the labels. Otherwise, you make your train set and your test set. You're going to need the both of them. Don't train on all the data you have. It won't work. It simply won't work. And if you make a validation set, make sure it is exactly what you're interested in. For instance, for a recent application, we had all Petri dishes, right, where they grow bacteria and fungus and what have you in there. And they wanted us to say, well, this pixel, this is this type of fungus, this pixel, this is a bacteria, stuff like that. So when you make a validation set for something like that, you have Petri dishes on which you train. You separate a couple of Petri dishes from the other Petri dishes. You don't separate pixels from other pixels. Why? Because if you're going to use this data, you will have a new Petri dish and not a new pixel. So when you make these separations, it's really important that you make them as you will use them. And then you choose your error function. When you have working in a company, you are talking with clients, this will be different than when in Kaggle competition. In Kaggle competition, Kaggle says, like, this is what you need to optimize, this is the number, then it's clear. Otherwise, you better choose an error function which is really suited for the problem. So you can look it up. There are already many error functions available. And for deep learning, you should always optimize the error function which you're going to use. So this might be pretty trivial, but I thought I'd mention it anyway. And then the next step is to make your train and validation curves. This is typical for any machine learning problem, but it's really important. This is one of the first things you need to do, because this is what you're going to use to see how your algorithm is performing, what you need to change, what you need to improve. What you do is you find the error function and you evaluate your network on your validation set and on your training set. And then through the training, yes, you plot out what performance the algorithm achieves on the validation set and the training set. That's the second step you need to do. Why is this important? Because you want to fight both underfitting and overfitting. Does everybody know what underfitting and overfitting is? All right, cool. So if you have made your two plots, you want to be in the ideal range, which is where your algorithm performs very well on the training set and on the validation set. So at a certain point, your algorithm will start overfitting. You want to be in the ideal range. This is especially true for deep learning. There's a specific reason for that, is that because your models have millions and millions of parameters, and often you only have like thousands of data samples. So you don't want to overfit. When you overfit, it will perform horribly. And this Joshua Bengujo is one of the big guys in deep learning, and this is what he says. If you want to make your networks, you need to make them bigger and deeper, bigger and deeper, bigger and deeper, until you overfit, which you can see on those plots I just showed you. And at that point, you start to regularize. You regularize, and then again, you can see on the plot, your errors will start to lower, and your validation scores will again start to fit more with your training errors. At this point, you just make it bigger. More layers, more parameters, more everything. And you rinse and repeat this, and this is the way to do deep learning. We think, at least. And he agrees. So, we already did the first two steps, right? So, we started our competition, a small competition, and we decided, we split our data set, right? We know how to make our plots. Then start with my first architecture. So for this, always use the standard components. Use conv layers, convolution layers, dense layers, max pooling, and dropout. Why? This is the important part in deep learning, because you want to fight those vanishing gradients. You want to be sure that your gradient goes all the way to the bottom. And this you can do through sparsity. And this is what they discovered in 2012, that you really need the sparsity in order for your gradient to really go through all the layers and also train the bottom layers. Yeah. And why sparsity? Well, I'll try to explain it. So if you have your neural network here, right? Some of the nodes are responsible for finding some type of signals inside your image. Yeah. For instance, here we have a cat node on the bottom, and we have a face node, and we have diagonal line nodes because it's closer to the image. Say I show the image of a cat, right? Yeah? Am I going too fast? Okay. So I showed the image of a cat, and at that point, I don't want my face node to optimize, to change parameters. Why would I change the parameters of my face nodes? Right? Because my face node has nothing to do with the cat, so I mainly want to focus on the cat node which needs to optimize. And to do this, I need the sparsity, in which the gradient doesn't go through all the connections. See, like if you have on the right, if your gradient goes through now, you only access certain nodes inside your neural network with your gradient, so only certain nodes will optimize, and this will make sure that your cat node is not forgotten, your face node is not forgotten, while you still optimize your cat node. I see you're frowning. Is this clear? Okay, cool. Yeah, if you have questions, please ask questions. I love questions. So, yeah.
It's purely random, right?
Hmm?
The dropout is random.
Yeah. So dropout is one way to do this. Dropout is purely random. You just turn on and turn off certain connections. This will automatically bring sparsity into your network. Dropout is one way to do it. Another thing is max pooling. So, say on the left you have your output of one layer lower, right? Then you max pool. So, which does that is that you look to the top 4 pixels on the left. You have 1, 1, 5, 6. You take the maximum, which is 6. 2, 4, 7, 8. You take the maximum, which is 8, etc., etc. Right? This is max pooling. Now, if you calculate the gradient, if you want to find the gradient of that 6, what will be the derivative of the 6? It's exactly the derivative of the 6 on the layer below. So the gradient doesn't go through the 6 to the 5, the 1, and the 1. Again, this is a way to achieve sparsity in your network. Yeah? Another way, which they saw in 2012, is that as an activation function, you need to use rectifiers. Why? Again, so a rectifier function is 0 when your neuron is negative, and it is the value of your neuron when your neuron has a positive value. So what does this mean? for the gradient. If your gradient comes from the right, if your neuron is active, so if the value is positive, it will go through to the next layer. On the other hand, if the neuron was negative, it will be 0 and your gradient disappears. So these 3 tricks, make sure that your network will stay sparse, and these are the way that your gradients will make it through to the bottom layers. Yeah, and this is what changed in 2012, and this is really important. If you want to use deep learning for these Kaggle competitions, this is the way you start. Convolution layers. Everybody know what convolution layers were, right? I said in the beginning. Yeah. Okay. Cool. For convolution layers, it's also important for your very first architecture. Don't make them too big. There's no reason to make your convolution bigger than 3 by 3. Why? Say you have a 3 by 3 layer. These 3 by 3 layers, they are connected to a receptive field of 3 by 3. As you can see, 1, 1 there is connected to 9 neurons on the layer below. A 5 by 5 layer would be connected to a 5 by 5 receptive field, right? Now, if you would stack 2 3 by 3 layers on top of each other, you also have a receptive field of 5 by 5. But in order to do so, you only need 19 parameters instead of the 25, right? So for your convolution layers, never use stuff which is bigger than 3 by 3. I say never, actually it's not really true, but in general, 3 by 3 is enough. You never need bigger convolutions than 3 by 3. Finally, you need to choose an output function for your very first architecture. If you want to optimize log loss, you need to choose softmax. If you want to optimize cross entropy, choose the sigmoid function. If you are looking for a regression problem, you need to choose an identity. This is to make sure that your gradient goes clearly through the very first output function. This is very mathematical. I'm not going to explain why, but in all cases, if you would calculate the derivative of a softmax, of a log loss after a softmax, it's very neat. And this is the reason why you always stick to the output function which corresponds to your error you're trying to optimize. So now, ta-da! Here we have our very first architecture, right? All the stuff we know is in here. We have max pooling, we have dense layers at the end, we have convolution layers, never too big, 3 by 3 is fine. Max pooling. This will give you about 1 million parameters which you need to tune. 1 million parameters, usually you have about 10,000 of data points. You can go 100,000. Last Kaggle competition we had 500. But that's about the range where the deep learning works perfectly. Or billions is also fine, it will work. But 1 million parameters is more than the number of data points you have. So this causes certain issues which you need to tackle. Now let us optimize and see what this is all about. Gradient descent was very clear for everyone. The ideal case, the perfect case, would be if you would take our entire train set, yeah, and use this entire train set to calculate the gradients and then take a step in that direction. Unfortunately, if you have a data set of 10,000 of images, for instance, our machinery is usually not big enough to deal with something like that. So this is the ideal case, but this is not a practical case, or GPUs are not big enough, or CPUs or RAM. This is a problem. So what we typically use is we use batches. We take a random sample of the training set, we use this batch to calculate the gradients, and this is called stochastic gradient descent, which probably you all heard of already. And because you only take batches from the train set, it's important that you use methods which average this gradient over multiple steps, which you can use momentum methods in order to achieve that. But what is very important, what we found works best is the Adams update rule. And since you're not in the ideal case, since you're not in the fully gradient descent algorithm, you need to use these multiple gradients, not the one from this batch alone, but the ones before, in order to have the best update step for your parameters. And something which is very important to keep in mind is that you're looking for a local minimum with your network. You're not looking for the global minimum because you have so many parameters, right? 1 million parameters, 10,000 points. If you're looking for a global minimum, your network will look like the one on the right. It will be so bad at generalizing that it will behave horribly. It's not what you're looking for. Okay, this is very important to keep in mind because a lot of people make a mistake in this, but you want generalizations. Generalization is what you're looking for. So, we know how to optimize this. Yes, we have our network. The next step, initialization. What are the initial parameters? This is something where a lot of academic research has happened, and it's very important. So this is really the difference between like an 100th place in a Kaggle competition and a 20th place, this stuff. When you choose weight matrices for your convolution, you need to use random orthogonal and initialization with the correct amplitudes. The reason is very mathematical, again, unfortunately, but this is to make sure that your information is not lost when you go up in a network, because orthogonal matrices, they don't they don't compress certain dimensions of your data. And most libraries already provide this, so this is not something you need to implement yourself, luckily. This is for the weight matrix, but the output layer is different, because you have prior information. Your output layer in the beginning, for instance with log loss, needs to give equal chances to all your outputs, right? Everything is equally probable in the beginning because your network is not trained yet. That's why your top layer should be initialized with zeros. Yeah. This might sound counterintuitive, but this is the way to do it. This makes sure that the first step will almost only train the top layer. And then you have the bias. Bias is the thing which you can use in the beginning to select how sparse your network should be. So, for instance, you use rectifiers. Yeah? If you have a random network, it means the activation of all your neurons will be randomly scattered over your axis, right? So about half of them will pass through the neuron, and about half of them will not. Is this clear? Right? So the bias will shift this distribution to either the left or the right. And if you go more to the right, if you have a positive bias, this means that your network will start off less sparse. If you go more to the left, this means your network will start off more sparse. And so you can tune the network on how sparse you want it to be initially using the bias. Think about your initialization. It's really important. I cannot stress this enough. I've seen tons of thesis students like showing me their code, and I look at initialization and say, like, what did you do? No, this should be, Yeah, you know the feeling if you have had students. Okay, so our first architecture is now properly initialized. This means we can probably start doing some really cool stuff with it. First question, does it work? Because at this point you've probably written tons and tons of codes. You're like 1,000 lines of code deep into the Kaggle competition, deep into your problem. You're going through the mud. Does it work? The first thing to test is train on one sample. Yeah? If your algorithm should be able to completely overfit on this one sample. If it does not, there's something wrong with the optimization. If it works on one sample, it should be able to train on 2 samples as well, because then it needs to give different labels to the 2 different samples. And if that works, it means your information can go all the way through your network and in the end predict it correctly. So in both cases, it should overfit completely. If it does not, it means there's a bug somewhere. This trick is so handy. This saved months of my life probably. Okay, everything is set. We have a gradient descent method. The next thing is the learning rate. You want your learning rate to be about right. You don't want to overshoot, you don't want to learn too slow. Look at it. Usually learning rates are about between 1/10 and 1,000th. And again, you can calibrate this using those plots I showed you before. So you have your plots on your train set and your validation set. And then you can go like you used to do when you went into the forest and look for leaves. What does my leaf look like most? If it looks like the yellow curve, well, your learning rate is way too high. If it looks like the green curve, it's still too high, but it's rather okay, since it's not going up. The red line is what you want to have, and the blue line is probably too slow. This is, of course, very theoretically. This can only be learned through practice, I think, or just by experimenting. Now we have our first network. It trains pretty well, probably. But this is one of the first things you need to do additionally, is smurf your data. Smurf means zero mean unit variance. So you make sure your data looks like standard Gaussian distribution. The mean is in the middle, is 0, and the variance, standard deviation, is 1. This is important in neural networks. This trick is very old. I think it goes back to the 80s. This was already very well known about neural networks. It still applies in deep learning. And some smart guys at Google, a couple of years ago, 2014 I think, they had this idea. Smurf all the things. Everything needs to be zero mean unit variance. It's very important. So what they invented was batch normalization, which basically is zero mean unit variance inside your network. And when you think about it, it makes total sense, because for this layer, the output from this layer looks like the inputs, right? So if this is an entire neural network, this one step less is still a neural network. Yeah? Makes sense? Yeah? Okay, cool. So it's important that you also zero mean unit variance, whatever is coming out of here, and whatever is coming out of here, and out of here. And that's what batch norm is all about. That's why batch normalization is important. This is something you can add. It's in all the standard libraries these days, and that's why it works, because zero mean unit variance. Okay, now we are going to talk about regularization. You remember the plot in the big circle? You had one step, which is make your network bigger and deeper, and another step, which is regularize. How do you regularize these kinds of neural networks? Well, there are many approaches. One way to do it is with data augmentation. In computer vision problems, in computer hearing. This is yeah. So take for instance this image on the left. This is an image of a certain type of plankton, which I took out of the data from one of our competitions. This needs to be classified as zooplankton. I have no idea, really. And if you would rotate this image a little bit, it's still a type of zooplankton, right? For us, this is very clear. But for a neural network, it is not. It is something which you can have it learn. So if you have a certain image, you can rotate it. You can zoom a little. You can add some noise, add some contrast changes, all this type of stuff to do data augmentation. So instead of 10,000 samples, you will now have way more samples, and this helps regularization. So this makes sure that your network will generalize over more samples, because it has never seen a certain image exactly twice during the optimization process. Unfortunately, this data augmentation does not mean that it doesn't overfit anymore. It still does. It's amazing how it does it sometimes. But it still can learn samples by heart, even though it's rotated, zoomed in, contrast changes, everything. Another way to do regularization is by adding unsupervised learning. Some common methods include pseudo-labeling or ladder networks. I cannot go into more detail here, but you can look it up. Pseudo-labeling is essentially taking another data, taking your unlabeled data, labeling it with one network, and then have another network trained on those invented labels. What you will see then is that this new network will be better even if it trains on bad labels, which you are not necessarily sure they are true. Your network will still work better because it has learned on more features, which you have also features which are only visible in your test data, and not necessarily in your train data. Another trick we often use is insert a priori information into your architecture itself. So this is kind of unfortunate because if you remember correctly, before 2012, feature engineering was the big thing. Actually, feature engineering these days has been replaced by architecture engineering instead. So if you know your data has, for instance, rotational invariance for the National Data Science Bowl in 2015, we made sure our network was rotational invariant as well. This a priori information really helps to regularize your network. Another example is from this year's competition was we needed to estimate the volume of these heart chambers, right? Based on MRI images we had. So, for example, on top we have two MRI images. Yeah. The red blob in the middle is like a 3D model of a heart, and you can see that these two images have been taken orthogonally from each other. Yeah. Instead of our network having just to learn, if I see these two images, this volume of the heart will be about 70 milliliters. No, we say like, no, try to estimate the area of this one and the area of this one, and we will do a mathematical computation to estimate the volume instead, right? So this is a priori information. We know something about the problem. We know how to calculate volumes, and this a priori information will really help regulate your network a lot. But really, regularization, it's an art. So all these tricks, all these stuff, this is something you only can learn by doing, I think. It's pretty much like painting. Like, yeah, unfortunately, that's still the case. It's still a very new area of research, deep learning. And then rinse and repeat. Yeah. If you want to win a Kaggle competition, this is doing the stuff I just explained to you in the past slides, and repeat. Regularize your network, make it bigger and deeper. If it starts overfitting, regularize some more. If it starts underfitting, make it bigger and deeper, etc., etc., etc. Improve and improve and improve and improve your models. And in the end, when the deadline of the Kaggle competition is getting closer, it's time to ensemble. One thing that people often underestimate the importance of ensembling, but for a lot of errors, the average prediction will always be better than the worst prediction. For instance, in log loss, you have the so-called Jensen's inequality. And this means that if you have 2 points, and you take a point somewhere in the middle, it will perform better than the worst prediction you have. This sounds pretty bad. It's better than the worst one you had. But if you think about it, if you have many models which are about on the same level of accuracy, if you ensemble them, if you average them out, it means you are mathematically certain to do better than whatever you had before. And that's why ensembling is really important, especially in Kaggle competitions where like the real world doesn't matter. If you need computation time of weeks to evaluate a model, it doesn't matter. Just ensemble. In our case, towards the deadline of the competition, we often had about 100 to 200 models which we averaged. So these were the models which we were constantly regularizing, making bigger, etc., etc. These were the ones we ensemble in the end to make our final predictions on the test set. And it's important, so this is why you need your validation set. Your ensemble is optimized on your validation set. This means you don't know how your ensemble, how good it will perform, because you have no validation set left. But you don't need it anyway. You have an ensemble. You know the models it started with are very well. And you know you often have the mathematical security that it will not perform worse than the worst model you already had. So you can just train on your validation set and submit this. Even though you don't know exactly how good it will still perform better than the worst one you had. And then submit. Yeah, this is always the scary moment. In any of those competitions, you work on this for 3 months, and then you make your final submission, and you wait on the final scores, which is often around midnight, because we're not in America. They like to have like the deadlines American time. Yeah. Then some extra stuff I would like to mention. This, like, you really need to, with deep learning, take into account the computing time. deadlines are fixed. You have only 3 months, and it's very often you think like, yeah, but if this algorithm would not train for like 100 epochs, but like 1,000 epochs, it will be better, right? Yeah, it's true, but you know this. You don't learn anything new from doing this. And your time is fixed. If you let your algorithm run for 2 days instead of 1 day, it means you lost 1 day on an iteration you could have made, an improvement you could have made, which you didn't do, and you didn't learn anything new. The end performance you often achieve on a certain data set is not necessarily proportional to the training time you spent on your model, but it's proportional to the number of iterations you made, the number of times you went around the circle, which was regularization, make it bigger and deeper, etc., etc. That's the thing you need to do. You need to do iterations. Yeah. So if I can give you some major takeaways in the future, if you ever have time to do a Kaggle competition, this is the important part. Everything in deep learning has a specific reason. I hope I explained to you some of the reasons that behind some of the stuff which is done in deep learning. Another important thing is don't buy into hypes. I've learned, and I think it's pretty general across big data and machine learning. If it can't be explained in 1 minute why something works, it probably ain't working. If you cannot explain simply why a certain technique, a certain new activation function or a certain new architecture type, why it works in 1 minute, it's probably just skip it. It probably won't work anyway. This is something you often see in academics now, is that if they have a technique and then they publish a paper and it says like on MNIST, on CIFAR, it works that good and that good. Yeah, but PCA works on MNIST. It's basics. So don't buy into those hypes. But still, I want to give you some cool clues, which are now like the up and rising in 2016. One idea, new idea, well, new, it's like 6 months old, is to fight the vanishing gradients using skip connections. So if you have a couple of layers and you add an extra connection around those layers, which you sum up with whatever is coming out, and you initialize layers with zeros, this means that in the beginning of your training, your algorithm will only go to the right, because there's only zeros there. And this means that your gradient can go like this around, and it can continue on top. So you have no vanishing gradient in the beginning of the training. Yeah? Okay. This is very cool stuff, very cool idea. So this is why, if you know about residual neural networks, this is why, based on this idea, these skip connections. This is something we'll see more of in the future. Using this, you can go from deep learning with about 10, 20 layers to deep learning with 100, 200 layers. Yeah? If you further work on this idea and you have like stochastic skip connections, then you can go to neural networks with about 1,000 layers and still train. So you don't have the vanishing gradient problem anymore. Another thing is these wide convolutions. I explained to you earlier about the 3x3 and the 5x5 convolution, right? So another way to have a bigger perceptive field is by just skipping in between. So you don't increase the number of parameters, yeah? But instead you don't have the problem with the 5x5 as well. So you have the equal amount of parameters as a 3x3, but you have about the perceptive field of a 5x5. This is something I guess we will see more of in the future. So thank you for your attention. I see I went through the talk a bit too fast. So if you have questions, please ask me questions. I love questions, and I get some feedback on how my explanation was. Yeah, okay. Yeah.
When you do your ensemble at the end, do you see that your different models are uncorrelated, and then the ensemble is good, worthwhile, or?
Yeah. So that's something we noticed is that so your initialization has random matrices, right? Okay. So your initialization has random matrices. So what we saw is even if you train the exact same model twice, the results are often uncorrelated to each other. So even if you train the exact same model twice and you average, you will do better than only one of those models. This is because you don't optimize to the global minimum and you start off with a random point in your parameter space. So it's something we used before. And it's a trick you can use if you have like no time to go through the loop for a couple of days. You train the same model another time. Especially at the end of the competition, it's interesting when you have better models. Yeah?
Do you ever consider a stacking approach in the final ensemble? Like learning how to combine your base models?
Yeah. So that's what I mean. When I say you optimize your ensemble validation set, that's exactly what I mean. So in your ensemble you have some parameters. Usually we just choose like weights. This is this important. This is this important. Sometimes you go like this model is this good for this type of samples. This model is this good for this type. So that's what you train on your validation set indeed. Yeah. It's a very big part because then you're not sure you do better than your worst model, but then actually you can go very low into your inequality. Yeah?
How long does it take to run one neural network? And can you give some measurements and how, when you look at the Kaggle competition, how long does it take to do a training? What kind of measurements are we talking about?
So what we typically do is, since we do this outside of office hours, we make sure that one model is trained in about 24 hours, or a little less, because so that when you finish, then you go to bed, and when you go back, that's about the time it should be finished training your previous model. So that's about one model. We often have a couple of GPUs running. It depends on the first competitions. It was less, but we invested the money we won into more GPUs. So now it's a bit more GPUs we have running. But that's in the beginning. In the beginning, you want to keep your models very fast, so you can iterate really fast. Towards the end, it's more worth it to like have a model which runs for like 5 days or something. Because if it's really good, if you know it will be really good, then train it until the point you really want it to be.
And how long does it take to go from just to go once through the neural network? So to get one.
So that really depends. The smallest models will be about 50 milliseconds on a Tesla. On a 680, it will be around 100, 200 milliseconds per sample. But that's per sample, so not per batch. Per batch is then 100 times longer. I don't know, 10 seconds, something like that.
So how many can you do in a day? How many would that be in a day, I presume?
Usually go about 10 or 20 epochs. But it really depends on your architecture. If you try something really fancy in the beginning, so if you say like we have this new layer we want to do, like which multiplies these two stacks in the beginning, it's not optimized, so you lose a lot of time. But then you can optimize and see like here this takes a lot of time to compute, or maybe this is not even computed on the GPU but on the CPU. So this is I don't think you can have a general rule on that. We just say like one network should be about 24 hours in the beginning.
Maybe a philosophical question. So where you see the limits of deep learning compared to other AI sort of goals, such as understanding the relations between entities, understanding why things have happened and that sort of thing. So how you see that compared to deep learning, and where you see the limits or extensions of deep learning?
So right now deep learning is very interesting for all types of media. But for instance, like for databases, I haven't seen any convincing arguments why you would use deep learning if you want to look through a relational or a graph database. So it's really only data. But apparently companies like Google and Facebook, they are investing a lot of money into this deep learning stuff. And if you look, like for instance, the Google DeepMind, with the Go example, they used these convolutional neural networks for something completely different, which was a board game. And my research is in robotics, mainly, So what I see in robotics is that also a lot of people are really interested in using deep learning for robots. So having robots learn how to look at the world and interact with the world just using neural networks. Like the biggest problem with deep learning is that it's a big black box. You have no idea what is going on inside there. Like this LSD thing was originally developed in order to deal with that problem. So for instance, right now you can see what a computer would imagine by what is I think it's a mosque, like with the domes and stuff. But other than that, it's really just a big black box. And yeah, I think that's really the limit. If you want to know how your algorithm is working, that's when you don't use deep learning stuff. Yeah?
Could it be interesting to train like a general model and then more specialized models? For example, you have a model that can have dogs, cats, but 1,000 different mushrooms, and then you just delegate it to the specialized model.
Yeah, this, for instance, for the competition, which was about measuring heart volume, we had models which specialized in really small hearts and models which specialized in really big hearts. And in the end, when you ensemble, you just throw them together and you will get an answer for any heart. Even also you ensemble together with models which do all the hearts. So yeah, the specialization is also something which we saw improved some things. But it's not like a magical solution, I would say. Other questions? Yeah?
It feels not like there's, you depend highly on trial and error. When you say, well, we have a simple process, just as much iterations as you can, you should do it. So does it mean that the Kaggle competition is won by the team with the biggest cloud infrastructure?
So you could say like I also think there's lots of alchemy behind it. It's kind of what I like about it. It's like this exploration thing, and it's really like when people learn how to paint, cooperative painting. There's something you need to learn how to see and what to do in certain types of situations. But it really not depends on the computation power. So, like, I'd say you need a GPU, at least a pretty good GPU, in order to compete in a Kaggle, or in order to win a Kaggle these days about computer vision, but not anything more than that. So, the other competition where we came in second, we lost to a team of 2 persons with. I don't know, they had a simple GPU, or they were even running on Amazon clouds. So yeah, it's really doable. What you need to do is just be very good in what you're doing, is know how the stuff works and always see where you can tune things a little bit better inside your model. Yeah?
Jonas, can you say again the number of days you need to end in the top 5 on a Kaggle? You know, what kind of investment are we talking about? The first time you won first place, it was like 7 people, 6 months.
No, 3 months. 7 people, 3 months. But we do this outside of working hours, and we're not working every day on those things. And we're also limited by the number of GPUs. We have constantly fighting over GPUs. In time investment, I would say if you have like, what is it? 1 person, say 10 hours per week, 2 persons each 6 hours per week for about 3 months. And then you should, then you can win competitions. That's a big investment, I know. But it's worth it. So there's also prize money to say, hey, you did a very good job at the end. Which I can invest in more GPUs and win more competitions. It's also kind of like, you know, this heroin cycle, like, you know, your first trial and yeah, kind of. Yeah?
Can you maybe create a deep learning solution to win Kaggle competition?
This is the solution. The thing I just explained is the solution. Yeah. What you mean, like a deep learning thing which writes your algorithm in order to win? That would be so cool. Yeah?
Are there any serious open source implementations of deep learning?
Yeah, so we only use open source implementations because we're in academics. I would advise using Tiano with Lasagna, but I know people, because it's Python, but if you like, there's also Torch, which is in Lua, and Café, which I think it's called Café, which is has C bindings, if you're more familiar with those. But But yeah, stick to the open source. I think especially in deep learning, almost everything is available open source. From the new academics papers to like the big libraries everyone uses. For instance, Google TensorFlow. Google also made it open source because they knew that they had only to gain with open sourcing their framework.
And which one did you use in your last Kaggle competition?
We used Tiano and Lasagna because Lasagna is something we developed in the lab originally, so that's what we use.
How do you write your models to this?
Sorry?
How do you write your models to this? Is it a pickle or?
Your models to this? Yeah. So a model is basically like a configuration file which says my network looks like this, and these are the parameters I train it with. And once you have the parameters, you dump the parameters in a pickle file on a hard disk somewhere.
And is there any work? Is that? I'm trying to wonder if there's work to make some sort of common network structure that people could say, oh, I'm sick of using TensorFlow, I want to take my existing models and load them up in Tiano. I want to try Torch, so I'm going to take the existing arcade dump maybe.
No, it's not. It's possible. So I reverse engineered a couple of neural networks from Café to Lasagna, and it took me about 8 hours or something to do so. So on one hand, it's possible. If you really like something, you can do it. But on the other hand, it's not easy to do. It takes some work. It's unfortunately the case. These are, if you want to know the backstory, so they have two academics labs, once in Montreal, once in Toronto, in Canada, really close to each other. They were really big into deep learning. They were doing neural networks back in the 80s already, and they have two competing libraries. Of course, they should not be compatible. Yeah. More questions? Yeah?
Very technical question. On the slide with the residual networks, why did the last layer have zero weight initialization?
So you want to not, the vanishing gradient is a problem you want to solve, right? So you want in the beginning your gradients to go all the way to the top of your network, right? And in order to do so, if there would be outputs coming out of the zeros layer, there would be gradients going back into there. Yeah? And then you would end up with two gradients, one very noisy, one very clear, merging together. That's not very good. So if you start off with zeros in the beginning of your training, your gradients will nicely flow all the way through the network up to the top. Yeah?
So it's not just the top layer, but also all the layers in between.
Yeah, this is like the very basic version, but like this is like the skip connection ID. So you have a connection which skips a couple of layers, and the bottom one of those layers is initialized with zeros. Yeah. Okay. Okay.
No last question.
Okay. Very much. Thank you for your attention.